Happy Thursday. Tomorrow's still going to be kind of the same, 50 minutes. I'm not going to try and cover the second lesson I wanted to cover this week on Friday. If I need to later in the semester, I'll extend to Friday to get caught up, but for right now, we should be fine. So it looks like this week we're only going to cover one thing, geometry in space. So let's take a look. So this is an extension from Calc 2. Right, so Calc 2, you start to look at parametric equations. Well, we're extending that now to 3 dimensions. Right, we're also going to start to look at what are known as surfaces. So these are 3-dimensional shapes. Right, the most common surface is a plane. Right, so the XY plane is actually a surface. Another common surface, sphere. Natural extension of a circle, right? So circle centered at the origin of radius r, remember, had equation x squared plus y squared equals r squared. Sphere centered at the origin, radius r, x squared plus y squared plus z squared is equal to r squared. Natural extension. We will also look at cylinders, right? Typically, you think of a cylinder, and what you think of is what's known as a right circular cylinder. Right, so something like that, or rotated to be along the y-axis or the x-axis. It's not the only type of cylinder. Cylinder has a specific definition. I actually don't remember what it is off the top of my head. Let's look it up. I think it's in my notes. I hope it's in my notes. I don't know if that file hotkeyed. Lines and planes, quadric surfaces, cylinders. Yes, okay, I do. So let's go ahead and copy that. Oops. This is also a cylinder. Right, so the definition, it is in the video, set of lines parallel to a given line passing through a given curve. It's known as a cylindrical surface or a cylinder. Here we have a set of lines parallel to a given line, and they pass through a surface. Hence, it's a cylinder. Parallel lines are called rulings. Here, it decides to sink. Here's another cylinder. Uh-oh. We've been lied to our entire lives. Like I said, the most common type of cylinder you think of is a right circular cylinder. times. Love math. By the way, remember back in algebra, even in pre-calculus, right, you studied graphs? Yeah, they're not actually graphs, they're plots. A graph in mathematics is something completely different. It's a set of vertices and edges. There's an entire branch called graph theory. So this is not a graph, this is a plot. So when you're graphing functions, you're actually plotting functions. We've been lied to our entire lives. How can I ever trust anyone again? You can't. You should always want to see the proof yourself. Right. The easiest surface to deal with is a line. Three-dimensional line. Find a set of parametric equations for the line passing through the point 1, 2, 3, parallel to any line with direction vector 2i minus j minus 4k. Then we're asked to determine which of the points A, B, or C lie on this line. And then we'll go ahead and use Mathematica for the first time this semester to plot the line. Right. So you guys are lucky. When I was in school way back, when dinosaurs still roamed the earth, we had to actually sketch these plots by hand. Have you ever tried drawing a three-dimensional plot on a two-dimensional piece of paper? It's not easy. Now we have technology, but of course we still run into the same problem. That is a three-dimensional surface on a two-dimensional screen. Mathematica tries to deal with that by letting you rotate it, as we'll see. But that still obviously has the inherent problem of you're still trying to view a three-dimensional object on a two-dimensional screen. And 3 dimensions isn't even the highest we go. We go to 4 dimensions. And our puny three-dimensional brains can't even comprehend what the fourth spatial dimension looks like. When trying to find parametric equations of a line, whether it's two-dimensional, three-dimensional, four-dimensional, whatever the number of dimensions, two things you need. You need a point on the line, and you need a direction for the line. Right? Point slope form, right? You have a point, you have its slope, which gives you a direction. Same concept. Well, we have both, right? We have our point. We have a direction. We know it has to be parallel to that direction vector. So that's its direction. In this case, the direction vector does not necessarily have to be unit. This is how you would find the parametric equations of the line. If none of the components of the direction vector are 0, we have symmetric equations as well. We just solve each of the parametric equations for t. Obviously, that t has to be the same. So all of those would be equal. Those are your symmetric equations. And obviously, if even one of the a, b, or c is 0, you would not have symmetric equations because you're not allowed to divide by 0. All right, so using this idea, right, P naught, 1, 2, 3, V 2, -1, -4. That would be your parametric equations of the line, or parameterization of the line. Bless you. T is the parameter. It doesn't have to be T. You can use anything. It's on the other side. It's over here.
Got it? Got it.
That was designed this room.
Wasn't really interesting. Speak to.
Not really. That should be good. It's a column right there. Now we have to determine which of 3 given points are on this line. There are two ways to go about this. You could find a parameter t that satisfies the x, y, and z coordinates simultaneously. Or we can look at the symmetric equation. And both for y and z, we're dividing by a negative. That's why the order is flipped. With the symmetric equations, to test if the point's on the line, just plug in the point and make sure the symmetric equation is satisfied. All right, A was 3, 1, minus 1. So is this a true statement? It is, right? You got 1 equals 1 equals 1. Perfect. A is on the line. Now we just do the same thing for B and C. And we say the same thing. Is this a true statement? Well, let's see. Negative a quarter equals 3/4. No, why am I doing a quarter? That should be 9/4, shouldn't it? That would be negative a quarter and negative a quarter. B is on the line. C was 201. Half equal to 2 equal to a half. That is a contradiction. This means that C is not on the line. Right? Right, so let's take a look at plotting it. We're plotting a set of parametric equations, right? And it's three-dimensional, Command and Mathematica. Parametric plot 3D. Notice that the first P in parametric and the first P in plot are both capitalized. Look what would happen if, doesn't say how it turned blue, text turned blue. That means it is not a recognized command. So I'm going to try and store this as a variable. Brackets. Braces. Do your X equation. 1 plus 2t. Then the Y. Then the Z all separated by a comma, right? Let's go up one more. There we go. Now, oops, why did you do that? We need to give a domain for the parameter. Doesn't really matter. Let's just start off with minus 10 to 10, see what that gets us. Technically, that is all you need. Shift enter. Now the magnification is too large. That's what it gives us. And so there are a couple problems here. Biggest one being, which represents your X, which represents your Y, which represents your Z. Whenever it plots it, this will always be your Z. It'll use Z as height. Y will be the closest to the vertical as you can get. So this is our Y. And then X would represent depth. So in this case, it's simple, even if we rotate it, to know which is which, right? Because Z is minus 40 to 40, Y is minus 20 to 20s, X is minus 5 to 10. Oh, that's odd. Right. So notice what happens to the mouse as I scroll over it. It's going to let me rotate it. So this is how Mathematica tries to do the 3 dimensions on a 2-dimensional screen. What if you weren't paying attention and all of the values were the same? What's your X, what's your Y, what's your Z? That's a problem. I also don't like the fact that it's boxed, personally. So there are options we can adjust. First, I'm going to get rid of the box. Do this, I'm going to make sure that my box ratios are automatic. And then I'm going to set boxed to false. Shift enter. It's no longer boxed. Huh. That's still not really useful. To make it look more like the coordinate plane we're familiar with, I'm going to tell it I want the origin to actually be the origin, 0, 0, 0. Ah, now at least looks familiar. Still have that problem of what is X, what is Y, what is Z. So I'm going to set my axes label to X, Y, and Z. Ah, now I know. And I was wrong. The X is minus 20 to 20. See that? Oh dear. So apparently they set the X to the horizontal. I don't know why they did that. It's really odd. Now we know what X, what Y, what Z is. Not a big problem here. Try and stand it up. There we go. That kind of resembles what the coordinate system would look like. With certain plots, though, it's going to be really difficult to see the X, Y, Z, right? Because look how they're kind of like inside. You can also adjust the label style. Let's do bold. All right, so if I just do bold, right now all the labels coming out bolded. Also change its color to make it stand out more. A cool thing I learned about Mathematica is, as long as you know the RGB code, you can put any color in here you want. We'll be playing around with that later. I can also, by the way, change the color of the line if I really wanted to. Actually, will it let me do that with parametric? I think it will. Plot style, yes. So I can make the line black. I can make it dashed if I wanted to, dotted. Right? I have a lot of fun with it. Can also change its color to any color I want. And then if I ask for a screenshot on like a test, just try and get a good angle so we can clearly see what it is. For a line, it really doesn't matter. Any angle would suffice. But there are going to be certain surfaces where you're going to need a specific angle to really tell what it is. Write the equation of the plane passing through a point P naught and parallel to the plane 3x minus 2y plus 4z minus 5 is equal to 0. And then we'll go ahead and plot the plane. Again, there's going to be two things you need to find the equation of a plane. First thing you need is any point that's in the plane. We have one. Second thing you need is a vector perpendicular to the plane. This vector is called the normal vector. Typically, a plane is represented with a capital pi. Don't know why they use that, but that's the most common I've seen. This is the standard form of the plane. This is the general form. Go away, please. Thank you. You can get general form from the standard form. Right. Again, typically speaking, unless the problem specifies, it doesn't matter which form you give, either standard or general. Typically, we represent it in general form. Right. Even more typically, you'll see the D on the other side. Right. Well, for this plane, we're given a point. Right? So the plane passes through that point, which means P naught is in our plane. We are not given a normal vector. Or are we? We're told it has to be parallel to a specific plane. Perfect. But you're up front. Sure, everyone can see this. This is the vector. Equals the plane. Point that perpendicular. Tables everyone can see. Right? Here's our parallel plane. Parallel to the table. Right? For the vector that's perpendicular. What can you say about those two vectors? They're parallel, aren't they? Could we say they're the same vector?
Wait, say that?
These two normal vectors,
Yeah,
they're parallel, right?
yeah.
Isn't a vector parallel to itself?
Yeah.
So can't we just say these two vectors are actually the same vector? No, we're not interested in magnitude. All we're interested in is direction.
Okay, then, yeah, I guess you could. So why aren't we interested in magnitude?
Because I just care about direction.
Oh, okay.
All I have to do is find the normal vector to the given plane that's parallel. And we can use that as our normal vector. We could also use the complete opposite, right? If we just switch the direction down instead of up, still perpendicular. What is the normal vector for the plane 3x minus 2y plus 4z minus 5 equals 0? If it was any more obvious, it would bite you in the foot. What do you mean? Is it the same? Well, we want a vector, not the equation. Right, it's going to be a different equation because 1, 2, 3 may not be in that plane. So you kind of mixed up your component form and your IJK. Right, so if you're doing IJK be 3i minus 2j plus 4k, right? Or component form 3, negative 2, 4.
Can you say the question one more time?
Given that plane, right, 3x minus 2y plus 4z minus 5 equals 0, what's the normal vector? How did you get 3, negative 2, 4?
X, Y.
Look at the general form of a plane. Aren't the coefficients of x, y, and z the components of your normal vector? That's why I said if it was any more obvious, it would bite you in the foot. Right, once you have the equation of a plane, finding its normal vector is really simple. So we're going to take our point 1, 2, 3, and we know a normal vector for the parallel plane. We're going to use the same normal vector. So our plane pi has equation 3x minus 2y plus 4z, and now it's the d that's going to change. Right. To find d, it's negative a times x naught. 3 times 1 is 3, so negative 3. Minus by naught. Negative 2 times 2, negative 4. So now we have negative 3 plus 4 is 1. Minus 4 times 3. 1 minus 12. Minus 11.
I'm confused. How did you just get negative 11? Oh,
I just did it. I just did the arithmetic in my head.
gotcha.
Right? Or you could write it that way instead. Doesn't matter. And it's all based on aesthetics. How do you like it? Do you want everything on one side and have it equal to 0, or would you prefer to have your constant on one side and all of your variables on the other? Even when it comes to plotting it, it doesn't matter what form you use. And I'll show you why. Right. So when we want to plot 2 dimensions, you'd use plot, right? And that command is y equals f of x, right? That's what your calculator does. Plotting in higher dimensions, same thing, except now it'd be plot 3D, and it would be z equals your multivariate function f of x, y, which we're going to study more in depth later. But wait, I just said the form doesn't matter. If I try to use plot 3D, we're going to have to write this as z equals some function of the other two. So I have to solve for z. The reason I say it doesn't matter is because I do not like the plot 3D command. It does weird things. If I try to extend the range, it actually like gives cutoff planes and just makes the graph look hideous. And I've not yet found a solution to get rid of those. So instead, I use the command that lets me plot relations. Which is the contour plot command. Since we're in 3 dimensions, it's contour plot 3D. Now I have to do is enter the relation. 3x minus 2y plus 4z. And this is why I said it doesn't matter. Because if I do minus 11 equals 0, or I say equals 11, the same bloody relation. Now notice, I didn't do a single equals. I did a double equals. In Mathematica, single equals is telling Mathematica you want to store something as this value. A double equals is a test. Right, so putting the double equals, I'm saying it's the set of points x, y, z that satisfy that equation. Obviously, when you're plotting something, that's what you're plotting, right? A set of points that satisfy an equation. We now need the domain. We have 3 variables, x, y, z, so we need a domain for all 3 variables. Let's start with minus 10 to 10 all the way around and see what we get. And again, that's technically all you need. And this is what it will give us. All right, so it's giving us a little bit of a cut. Right up here. I'm not sure if we can actually correct that. We can try to extend everything out. I try to keep everything the same, so let's try minus 20 to 20 all the way around. Let's just see what happens. I don't think it's going to make a difference. Yeah, it really is. But actually, man, it works, right? Because now I have another cut. Because remember, a plane's going to extend forever. If I do undo. There we go. I'll just stick with that. First thing I notice is, oh my God, those rulings are hideous. I immediately want to get rid of those because they just look hideous. So I'm just going to set mesh to none. That looks better. All right, now I go. I don't like that box. I want it to actually look like a coordinate system. Right. So same thing as before. I'm going to be safe and just set box ratio to automatic. I'm going to turn boxed off. And set the origin to 0, 0, 0. That's what we now have. Let's go ahead and label our axes. And I'm just going to go ahead and rotate it to make it look more like coordinate system of XB depth, which of course is going to change the shading. And of course, now this points out perfectly what I was talking about. The X label is now hidden within the plane. I can't see it on my screen. I don't know if you can see it up there. I don't know why I did another arrow. I set it to bold. That didn't really help. Oh, I can see the X now. I know where I can at least see where it is. It's now under the -5, which is annoying. Huh. I move it. There we go. Now it's not on. Now it's not actually hidden by the -5. I can just barely see it on my screen.
I can't even see it.
Right. That fixes that, but now the Y and the Z are not visible, right? So just play around with it. I think we found one semester that green generally worked. But we can also change, I think. Can change the contour style. It may not be that. This is where it gets a little weird because of how it shades three-dimensional. Even though I have the contour style set to white, that is clearly not white. Well, serves my purposes. So I'll just leave it. And so you can really mess around with it. Now I want the equation of the plane that passes through the points 1, 2, 3, and 3, -2, 1. That is also perpendicular to the plane. 3x minus 2y plus 4z minus 5 equal to 0. Same plane, same normal vector, right? We would all agree that this is perpendicular to this plane. Normal vector plane. What can you say about the two normal vectors? Normal vector is also perpendicular, right? Yep. So what we want to do for our plane, again, it doesn't directly tell us a normal vector, but we know that its normal vector is going to have to be perpendicular to 3, -2, 4. We have 2 points in the plane. The normal vectors of the plane would also have to be perpendicular to any vector in the plane, right? So it has to be perpendicular to 2 specific vectors. The normal vector to 3x minus 2y plus 4z minus 5 equals 0. And the vector whose terminal point or whose initial point is P0 and terminal point is P1. How do we find a vector perpendicular to 2 vectors? Cross product. Is the order of the cross product going to matter? No. It's just going to give a 180-degree rotation, right? And since we don't really actually care about direction, we just care about whether it's perpendicular. Doesn't matter the order in which you take the cross product. What do I want to call this? Called N perp to represent the normal vector of the perpendicular plane. Vector in the plane. Remember how to find component form of a vector that has an initial point and a terminal point. So what would the component form of this vector be? So what's the component form? Works for me. Let's actually simplify it. When I'm trying to find a vector that's perpendicular, we don't care about the magnitude, do we? We care about the directions. So why not use 1, -2, -1 instead? Same direction, right? It's just shorter. But who cares? I sadly can't make such simplification on n perpendicular without introducing fractions. Right, so I'd rather deal with larger numbers than fractions. Normal vector to our plane of interest is then their cross product. I did in my notes. V cross n perp. But again, the order doesn't matter. -2 times 4 minus -1 times -2 would be the first component. So that'd be what? -8 minus 2, -10. Then the middle component would be the negative of 1 times 4 minus -1 times 3. Since I know it's a minus, I'm gonna actually flip the order. It'll be -1 times 3 minus 1 times 4. That's what, -3 minus 4, -7. Right. Final component will be 1 times -2 minus -2 times 3. -2 plus 6 is 4. There's our normal vector. Now, purely for my own personal reasons, I'm going to use the opposite direction. I hate negatives. The fewer negatives, the happier I am. So I'll just use 10, 7, -4, right? Still perpendicular, right? All I did was rotate it by pi radians. So our plane would have equation 10x plus 7y minus 4z. Now we have to determine the pick either point, P0 or P1. It does not matter. Right? It just has to be a point in the plane. I'm going to go with P0. 10 times 1, negative that, right? Negative 10 minus 7 times 2, negative 14. That's now negative 24. Minus negative 4 times 3, negative 12. Negative 24 plus 12 is negative 12. D is minus 12. And there's our plane.
Can you go over one more time how you got -12?
Negative 10 times 1. Right? You do negative a times x naught. So that's negative 10, right? Minus b times y naught. So it'd be minus 7 times 2, minus 14, right? That's negative 24. Minus c times z naught. Negative 4 times 3, negative 12, right? So because it's minus, that's plus 12. Negative 24 plus 12. Negative 12, right? So there's the minus 12.
Thank you.
Again, you can write it in standard form and then just expand it out. And you'll get minus 12 out of that as well. Work smart, not hard. For the most part, that's the only thing that's going to change. My options are most likely going to stay the same. I might just have to do another rotation, but I doubt it. What, 10x? What we say it was 10x plus 7y minus 4z and then minus 12, right? Shift enter. You have to rotate it. That looks pretty good. Oh, wait, actually, it does look like it did change the rotation. No, it didn't. Okay. Right, you can rotate just to kind of see different angle, right? But I'm going to keep the rotation just about there. That's good enough for me. And yes, I didn't have to change any of the settings, so perfect. I do number 4 in 5 minutes. Let's see how far we get. Hate these 3-day-a-week courses. I'd rather just have 2 days, an hour and 40 minutes each day. Oh, now you don't. Oh, there you go. Okay. So now we're given, we want an equation of a plane that contains these 3 points. Well, we have a point in the plane. We actually have 3 of them. We get to choose which one we want. But we do not have a normal vector. Or do we? Remember what we said for the last problem? A vector that's normal to the plane would have to be orthogonal to every vector in the plane, right? Oh, I found a typo. Typo fixed. I didn't have P not equals. Now I do. We can find 2 vectors in this plane, can't we? We're given 3 points. Does not matter how you pair the points. I think what I did was I said V1 is P naught P1. And that should be the same as what we just did, right? 2, -4, -2. And again, doesn't matter the magnitude because we're only concerned with directions here. So why not make that 1, -2, -1 as we did before?
Symbol exactly mean when you're like doing the regarding the magnitude there, just simplify.
Typically it means maps too. It can also be used as transforms, right? So I'm transforming it because I'm essentially picking a different vector. So I don't want to say equals because they're not equal, right? So I'm saying I'm transforming it into this vector because all I care about is direction. I don't care about its magnitude. For V2, I used P naught P2. You don't have to, right? You could have done P1 P2 or P2 P1. You could not have used P1 P naught. Because that would have given you 2 parallel vectors that has a cross product of 0. Or -2, -7. Oh, you bastard. I can't simplify that one without fractions, so. Normal vector for this plane would then be V1 cross V2, right? Your job is to make sure that you can get that cross product as this. Twelve, three, six. Of course, I'm going to use 4, 1, 2. Take out the common 3. We will pick up here tomorrow.